Welcome to this video. This is Mark Scythian, FAA licensed aerospace technician, airframe power plant and avionics certified. The date today is July 31st, 2017. The title of this lecture is DC Series Electrical Circuit Analysis. In this lecture, you will learn how to calculate the variables involved in a direct current DC series electrical circuit. DC series electrical circuits maintain constant current while allowing for voltage drops by means of resistors. In a basic sense, in regards to analog DC series electrical circuits, physical resistors are present which can be installed and removed by means of soldering and desoldering for repair or customization purposes based on required resistor ohms specifications. However, in the present day, DC circuits are not analog circuits but are digital circuits which contain operational amplifiers, MOSFETs, programmable logic circuits or PLCs, and digital wireless interfaces allowing for programming to change resistor specifications without actual physical interaction of the circuit. Digital signals processors, crystalline CPU, and PLCs allow for software control of DC series electrical circuits. Values then quantified using binary base 2 logarithm mathematics instead of decimal analog mathematics. Regardless to how advanced DC electrical circuits become, they still are bound by Ohm's law. Now let's proceed to two DC series electrical circuit analysis problems. Now here is a typical simple DC series electrical circuit. In regards to direct current, electrons will flow only from positive to negative. The negative represents the ground, and the direction the electrons will leave the DC power source is from positive to negative. The DC power source could be a battery, or it could be an alternator converting AC power to DC power. It could be a AC power source in a wall outlet, then rectified through a diode, then converted to DC, and then sent through a transformer and made into a specific DC voltage and total amperes. Whatever the source is, it's represented by the positive and negative symbols denoting a DC power source. So the rules for series electrical circuits are that the current, or the amperes, throughout every circuit will remain constant. When I apply to a circuit as in a voltage drop using resistors. So here we have the rules for resistors added in series is cumulative, so 45 plus 15 plus 50 plus 20 plus 90 would equal the total resistance of this given circuit. Ohm's law is E, or voltage, is equal to I, current, times R, resistance, in ohms. So the next step is to solve for the total current in this given circuit. So E is equal to I times R. We solve for I, so that would be E divided into R. We know the total voltage is 12 volts. We would then divide that into the sum of these resistors. Now, if this was a parallel circuit, you could not add the resistors cumulatively, but you would need to use the inverse summation rule, which I will explain in the parallel DC electrical circuit lecture. But this lecture focuses only on DC series electrical circuits. So once we calculate the total current, we can use the fact that series electrical circuits maintain constant current. So whatever our total resistance becomes from that formulation, we can then solve for the voltage drops. E is equal to I times R. So we know the current, we know the resistance, we multiply them out, we get the voltage drop. So the total number of voltage drops will equal the total amount of load going through the system, or the circuit here. So from that point, we can then calculate the power. P is equal to I times V, current times voltage, the power dissipation by each resistor. So the questions to ask to do proper circuit analysis for this given circuit are these questions here: total voltage, total resistance, total current, voltage drop across resistors, the current at the resistors, the power dissipation at the resistors, and then the total power. When we have a summation of all the values, they should all come down to zero by the end result, canceling out input to output. This is represented by Kirchhoff's law. But we can use Ohm's law to figure out most everything by obeying the rules of given circuits. So we know there's 12 volts. The total resistance, we know there's a total voltage of 12 volts on the circuit. Total resistance of the series circuit is by the summation rule of resistors in series, 220 ohms. Then we find the total current, 12 volts divided by 220, so that would be the total current in that circuit. Then all we have to do is find resistor 1, which I'll just give a little reference here. Resistor 1, 2, 3, 4, 5. So voltage drop across resistor 1, we simply take the total current times the resistance of resistor 1, 45 ohms, 1 multiplied out, 2.45 volts. We repeat the process throughout all the other resistors. The current, total current times the resistance value. So we have a total of 5 resistors, so we should have 5 different voltage drops, which we do. Now, the current at each resistor, well, in series circuits, the current will remain constant, so whatever the total current is also the current at each resistor. The power dissipated at each resistor, well, power in watts in DC electrical circuits is equal to current times voltage. So we know the current, and then we know the voltage drop. So we can calculate the power dissipation at each resistor using that methodology, which we have right here. So now all we have left is to calculate the total power. Is the total current times the total voltage. That would be the total power involved. And then to check the work using Kirchhoff's law, the total power is also equal to power dissipation at all resistors added together. So we can add them up and we also get the same value. So we know all of these answers are correct because the input power and the output power, when analyzed at each voltage drop, current flow, and power dissipation at each resistor, will equal the amount of input to output equaling 0. So when we add all these up, we get exactly this value as a check. So that completes the circuit analysis of problem number 1. Now we'll go on to problem number 2. In this one we have a battery source, positive, 2 negative, and then we have an on-off switch, and then it grounds back to the battery. A simple series DC electrical battery circuit problem. And as you can see here, when we throw the close the switch, this is going to cause electrons to go from positive terminal through the resistors in series and then ground to the battery, negative, completing the circuit. So again, we know that whatever the total current is, that will also be the current at all the resistors. E, voltage, is equal to I, current in amperes, times R, resistance in ohms. This will calculate the voltage drop at each resistor. So we can add 25 plus 15 plus 7.5. That will be our total resistance. We can take our total voltage, 12 volts, divide it by total resistance, then we'll get total current in amperes. And that means the current will remain constant since it's series. So that will be the current, total current will be the current at all the resistors. We have I, then multiply times R, we get the voltage drops. Same questions as the first problem. In the same methodology, we add the resistors since they're in series. Total resistance, we divide total voltage into total resistance in the series circuit. This is the total amperes. Then we multiply that times each resistor value. We get the voltage drop at all three resistors. And then the current will be constant throughout the circuit. It's equal to the total resistance, or total current, sorry. The total current will be constant throughout the entire circuit since it's series. Then we just take P is equal to IV, I current, times V voltage is equal to power in watts electrically. So we have a constant current throughout all three resistors times the voltage drops at every resistor. And we get the wattage dissipated at every resistor. Then we take the total current times the total voltage to get the total power. Then we check the work by adding all the power dissipation at each resistor. It equals the same value, so this is all correct. That completes this lecture on DC series electrical circuit analysis. Thanks for watching.